Okay, I'll be going over the bonus simulation for the final project for aerodynamics, which is an Ansys fluent simulation around an airfoil, which is a 2D simulation. And we will use fluent as given with air density of 1.2 kilograms per meters cubed, and the dynamic viscosity as 1.8 times 10 to the negative fifth. We'll need to plot CL versus alpha, CD versus alpha, and then CL over CD versus alpha. And then we're going to need to get the velocity and pressure contours at 0 and 10 degrees respectively, and then have varying -3 to 21 degrees with increments of 3 degrees for Reynolds number of 1 million. This number of 1 million we will use to calculate the inlet velocity magnitude. And, well, nothing to do but get started. So we're going to drag fluid flow fluent into the project schematic here. We're going to want to go to 2D analysis here. Now we can just go ahead and open a new design model or geometry. And for this, we're going to want to just basically search up the NACA 2415 before we do anything else here. NACA 2415. And if you scroll down here, you'll get your thing here on airfoil tools. You'll have a 4-digit airfoil generator. I did 200 points for the maximum efficiency. Make sure you close the trailing edge. And basically, if you plot this and then copy all this data down into Excel, just copy down this, put it all into Excel. C, Control V. This will be basically your X. This will be your Y. Then you're going to want to number your points. So this will be like 1. Then you can increment this as equals that plus 1. Then you're going to basically drag it down all the way to the bottom of the data. See, it's 201. Here at this point, we're simply just going to delete this. We're going to have named this at 0. Delete this value as well. This will all be 1 in the column before for the grouping. So you can just put 1, drag it all the way down, and then the last column will be your Z column, which, because we're working with 2D, Z will always be 0. And then once you have this, you can select it all, and then what I did is I basically just put it into a notepad like this. You'll have your grouping, point number, X, Y, and then Z. And then once you have this, you can file, save it to somewhere. I saved it to a final project folder. So once you have this, then you can go back to the Ansys design modeler here. Look at the XY plane. We're going to go to concept 3D curve. Then here, this is what we want the coordinate file for. We're going to go from coordinate file. You're going to go find your file wherever you saved it. Save it to my arrow final project. NACA full. As you see, our airfoil will be inserted right here. Now what we want to do is generate. And then we can go concept surface from edges. Go ahead and click the edge, apply, and generate once more. So see, there'll be a airfoil generated right there. Next thing we're going to do is get into the sketching. So we're going to want to go to arc by center here. P, and then make sure it's C and C. Then we're going to dimension this one out. Following along video, so this will put it to 7.5 meters here. And then we're going to go to the line tool here, and make sure it's an H for horizontal here. We're going to dimension this one out to be 15 here. 15 meters. And then basically we can just close out this shape, P, V, and C. You go here, H, make sure you see the C, perfect. Close that up. Okay, now that we have this general shape here, what we're going to do is create a couple more lines here. So we're going to go from here, make sure it's vertical. It says V. Then we're going to dimension this out horizontally from the y-axis. This will be 1 meter. And then what we're going to do is go to modify extend here, extend it to the top. We can just draw the line straight down as well. Make sure it has V and C. There we go. And then we'll add one more line in the middle of this airfoil here. It's V. We will then dimension this out horizontally once more, so that this is indeed 0.08, so 80 millimeters. And then we'll modify and extend this once more. And then we will once again draw a line P here, straight down. Make sure it's V and C. Perfect. And then that's basically all that we need for the lines. Next thing we're going to do here is go to concept lines from sketches. We're just going to select every single one of these points on the outside. There's an easier way to do this. I selected all these points, but essentially what you could have done is just go line from sketches, go here, click the sketch, apply, generate, and then what we're going to do is create a surface from edges here. We're going to select 1, 2, 3, 4, 5, 7. There's going to be small little points here, 8. There's going to be 1 at the top. To zoom in, you just hold right click and you can go into the section. There should be 9 total here. Generate this. And what Ansys is going to do is it's going to automatically assume that this is a solid body. So what we're going to want to do here is go to here, click the surface body, and turn it into a fluid body here. Generate it once more. You see now it's a little more transparent. From here, what we need to do is we're going to need to basically subtract the airfoil from the fluid. So what we can go to create Boolean here. We're going to go to subtract. Target body can be your outside body, and then your tool body, just double click and get to your other body. And then if we click generate here, we select the surface body here, you will see that the airfoil is cut out of it. So one last thing, or a couple more things we're going to need to do. We're going to need to basically just go to tools here and go to face split. We want the target face to be this whole section, and then the geometry, make sure this is on edge selection here. We're going to select 1, 2, 3, 5, no, not this, sorry. 1, 2, 3, 4, and the x-axis here. We're going to hit apply and generate. To make sure you did this right, you can filter faces. There should be 6, so 1, 2, 3, 4, 5, and 6. As you see here, there will be 6 faces. One thing we will need to change real quickly before going into the meshing is there's this little small horizontal element here. Zoom in. There's this and then this, so we can just select both of these, go to Tools, Merge, Apply. As you see now, hit Generate. It should become one solid line here. We're going to repeat the same thing for the bottom down here. So Tools, Merge this and this line, Apply, and Generate once more. And this will be a solid line as well. Now we should be ready to go and do the meshing. You can go ahead and close out of this if you need to. I just like to minimize it. I always like to update the geometry right before going into the mesh. Now you can double click on the mesh, let it open. Okay, once your model is loaded in the meshing software, what we want to do first before we do anything is basically suppress the line body so we don't accidentally select one of these lines instead of the actual surface. I did this a couple of times and forgot to suppress this, and it really led to a lot of mistakes in the meshing. So just ensure you do this first. And then first thing we're going to do is insert a sizing onto the mesh. And we're going to basically select all of these lines here. Not that. this. You're going to apply. We're going to go to number of divisions here. We're going to make this 200. We're going to capture curvature off, and we're going to put a bias on this. I put a bias factor of 50,000. Seems to work the most. And as you see here, the bias will get, or the it'll get finer as you go towards the airfoil. You'll see some of these are in the opposite direction. That's what this reverse bias here will be for. You're just going to select all the ones that are going the wrong way, essentially, and apply that. It'll minimize them, but you can see them if you just select this again. Nothing too crazy. So that's going to be the first edge sizing. We're going to do 4 total. So we're going to go to another edge sizing here. We're going to select more edges. Okay, and then for the second edge sizing, we're going to go from here, the top, here, and here. Apply. Oh, it has the other edges selected. I only want these 3. There we go. Once again, it's going to be number of divisions. We're going to go 150 here. Capture curvature will be off, and we're going to go with a hard behavior here. Once again, we're going to do the first type of bias. Go 300 bias factor here. We'll have to, once again, correct this reverse bias once more. These 2, reverse bias, apply. These look good. We're going to go back into mesh, insert another sizing. This one will be the top of the airfoil, the bottom of the airfoil, the basically right half of it, right section of it, and then these top 2. Selections. Once again, we're going to go number of divisions. We're going to go 150 again for this one. Capture curvature off, and then hard behavior once more. But for this, we're not going to worry about the bias. We're not going to worry about the bias anymore, actually. And then this one, you might have to zoom in. It's going to be these front panels of the airfoil here, and these front 2. We're going to go to number of divisions once more. We're just going to go 100 here. Capture curvature once more off, and also make this behave hard. So now we're going to insert the base class thing, which is face meshing. Just Control A to select the entire shape you have defined. And then, well, here you can basically just hit generate to generate your mesh. It should look pretty fine around all these sections. It might take a while. It'll pop up with this error. As long as the mesh looks like this, the overall calculations and simulations just still run perfectly fine. Basically, it's just trying to, there's like a sharp edge or one of the faces overlap a little bit, which causes this to pop up with an error message. But if we zoom in here, the mesh gets really fine around the airfoil, and you will see that this should be pretty well defined for it. Last thing we're going to need to do here is we're going to need to make some naming sections. So we can go ahead and select the edge here. Go ahead and hold Control, select all of these sections here on the upper outer edge, and name this inlet. And we're going to select these 2, name it outlet. And then lastly, we can select all 4 edges of the airfoil and name it airfoil. We have these 3 name sections. Basically, it'll say your inlet, your outlet, and then your airfoil should be considered as the wall, as we want to know the flow around the airfoil. So once this is done, we can minimize this. Go ahead and update your mesh. And now we're on to setup. So we're going to double click this, double precision. You can use any number of these solver processes. I recommend over 2. I'm just going to start with 3 here. If you do less than 2, it's just going to take a long time to calculate all the conversions. Nothing really bad, it's just it'll take longer. So we're going to let this load for a little bit. Okay, so now this is loaded. We can go ahead and check the models. I'm using K Omega. Then we're going to go to our fluid properties because we are given the properties in to the project statement. Essentially, it's 1.2. 1.2 for the density, and then it'll be, if we check right here, it'll be 1.8 times 10 to the negative fifth. So we can just go ahead and get rid of these. 1.8 negative fifth. And then basically using these to calculate the inlet velocity at the beginning. If we go to boundary conditions, we can check inlet is inlet, outlet's outlet, wall should be airfoil. Perfect. Basically, so to calculate this with the angle of attacks, instead of doing the magnitude normal to boundary, we're going to do components with x and y velocity. I'm going to be simulating 0 angle of attack, so if I go over here to this good old data I have here, you'll see that I have highlighted the two that we actually need to get the contours for, which I have below. So the Vx will be 15, Vy will be 0, because the angle of attack will be 0, so the sine will be 0 and the cosine will be 1. The velocity overall should be 15. So basically doing this, you'll get the Vx as 15 Vy. You'll basically just multiply by these two to get your x and y components of velocity. 15 is gathered because we want a Reynolds number of 1,000,000. And essentially, if you all that with the Reynolds number and the viscosity and density, you'll get about 15 meters per second. So we'll go 15 here, apply. Then what we're going to do here is I'm going to define some report definitions here. Right-click new, force drag. We want drag coefficient. Just name this drag coef. Like the airfoil. Okay. And basically, once more, we're going to create a new force report lift. Name this drag. Oh, sorry. Lift coef. Like the airfoil. So basically, these force vectors, best way to describe it is you'll get them from these two values here. For the lift, this will be a negative, whatever this is, for your x. This will be your y. And then for your drag, this will be your x, and this will be your y. And then this will remain the same sign that is right here, while in the lift, this will be your x, and this will be a negative of whatever this is in this chart. Basically, this chart, I just use formulas, simple. Excel calculates cosine and sine using radians, so make sure that you convert the degrees here to radians, which is why I have this multiplier right here. That way you get accurate values. Otherwise, your values will be all whack. So if we go back into this here, we have to find the lift and the drag coefs. So if we go down here, you'll see, oh, not save. There we go. Now we have both. What we're going to do here now is we're going to go to monitors and change the residuals a little bit. 1e to the negative 6 should be good for accuracy. Basically, you'll just get a lot of small numbers in these simulations, and having this extra residual criteria will help you to get better solutions here. We'll hit OK there. Now what we can do is we can go straight into the initialization. I like to do 100 iterations to initialize. Just makes it more likely to generate good data. So you're just going to let this run out. Okay, once the initialization is done here, we can go down to run calculations. I'm going to do 1,000 iterations. Running through all the increments, what I found is that sometimes 1,000 isn't enough either, so you can bump this up to, say, 1,500 to 2,000 iterations. Basically, you'll just keep going lower in a value. 1,000, you'll still get a relatively similar value. When I tested it, I got, for example, here I got around the CL over CD was around like 8.1 when it was 1,000, and then it went down to 7.4 when I went to 2,000 iterations and converged. So this is what I finally got for the end. So basically, if you want, you can keep testing it, make sure it converges at the end. But essentially what you're going to do here is you're going to run your calculations and then it will converge. And let me do that real quick. So you're going to hit calculate here. It might take a while depending on how many cores you use, how many solver processes. But I will come back when it's done. Here I'm in the middle of it. I'll just show that basically it will, this is the lift coefficient plot. You'll see the lift coefficient start to converge to one value. Same for the drag, and then you'll see the residuals all eventually going down to 0 down here. But you'll see that these kind of even out, and you'll see that they converged. It's going to run a couple iterations, or multiple iterations past the convergence point before it stops, and then you can go your drag and other things after. I'm going to let this load out real quick. There we go. After 180 solutions, I got a convergence value here. It might freeze up a little bit after you run them completely. Normal. Just let it load. Okay, now the calculations are done. Mine froze for a little bit, but you'll see 180 solutions convergence, as I said before. It'll write out the data. Now what we're going to do here, he wants the contours, so he wants velocity and then all the pressures. So I'm going to go here to new, name this just velocity, contours of velocity, velocity magnitude, compute, save display. You'll see here you'll have your stagnation point in the front, and then you'll have your low velocity in the basically like wake region of the airfoil here. Then he wants the other ones, so what you can do here is close this. You have your velocity, hit new one, static pressure, static pressure, save display. I already put all this into the Excel, so I'm not going to worry too much about what's going on here, or not worry about saving all these contours here. But when I did originally, I had all these named, so whenever I changed to 10 degrees, I just had all these and I just had to click them once more. But there you go, static pressure. You can go dynamic pressure. And then we can go total pressure, which you'll see a drop off in the total pressure towards the back end of the airfoil. Once you have these done, basically that's it for the contours that you need. Now we need obviously the drag and lift coefficients, so you can just double click this, compute. It'll write this out. And then you're going to go to lift coefficient here, compute, and it'll write this out. These values are a little high. Something's probably wrong with my meshing, but for generalization, first time around I got values in the 0.0s for the drag, essentially up to the 21 degrees, and then lift coefficients similarly low. Then once you get your drag coefficient and lift coefficient, you can calculate the coefficient of lift over the coefficient of drag. Basically create your general graphs here for each of them. And then once you can compare with the XFLR5 data as well on the same graphs. So you'll just create another graph for this versus the XFLR5, this one versus it, and then this one versus it. And you'll get 6 graphs total, I believe. So you'll have your pictures of your contours, all that. Just double check that I'm not missing anything. You'll increment it. At 0 and 10 degrees. So basically to change it, you just go over here to the inlet velocity here. Go back to here. You'll see I calculated it all. So 10 degrees. You're just going to take this as your X. And then the other one as your Y. This will be your X. And then you'll go back to your thing. This will be your Y. And you'll basically apply. And then you'll change your dimensions over here. So your X will be this. And your Y will be this value. Okay. And then for the lift coef, Your x will be the same value you had for the y on the other one, but negative. And then your y will be the larger value over here. Do this once more. Okay, once more. Then you can just basically initialize once more. Okay. Basically what you should see is that the stagnation point is going to slowly move around the airfoil depending on your angle. And the trailing edge might change a little bit depending on your angle as well. We snap back to when the calculations are done. Alright, now that the calculation is done for this one, just hit OK here. This one took 527 to converge. So as you see, as you go higher in the angle of attack, what I found is that the solutions to convergence generally goes higher. This is done. We can go take a look at the velocity once more. Save display, you'll see that the stagnation point ended up moving a little bit further down. And then you can do the same thing for the lift and drag coefficient reports. Go over to your Excel, copy it down, calculate the CL over CD, which you can use the general formula, lift over drag. And then, yeah, that's basically it for this, I believe. That should be all I needed. And then just make sure you get this data and then compare them at the end.